Tonight, we're going to explore something that sounds simple, but is actually one of the most mind-blowing facts in all of science. Empty space. You've probably heard that the universe is mostly empty before. Scientists talk about it all the time when describing galaxies, stars, and planets. But here's what most people don't realize. When you truly understand just how much nothing there really is, when you grasp that almost everything in the universe is empty space, it changes how you see everything around you. This is not just a small gap between objects. It's a vast, unimaginable emptiness that challenges our ability to picture reality itself. And by the end of this journey, you're going to understand exactly why the universe is 99.9% nothing, how scientists discovered it, and why this empty space is more important than anything we can touch or see. Before we go any further, if you enjoy this kind of deep exploration, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. When we look up at the night sky, the stars seem close. Each point of light appears near, as if the sky is a dome filled with bright objects. But the truth is very different. The universe is far larger than we can imagine, and the stars are tiny specks within a vast emptiness. Between each star, the distances stretch for millions, even billions of kilometers. Even in our own galaxy, the Milky Way, the stars are separated by immense voids of nearly empty space. This emptiness is not a few small gaps. It dominates the space around every star, every planet, every gas cloud. The universe, in its most basic sense, is mostly nothing. We often think of space as a stage for planets and stars, as if it were filled with air or some substance. But space is almost entirely empty. The air we breathe, the dust we touch, and the molecules we see are almost entirely absent outside planets and dense clouds. Even the atoms that make up every object we know are only a tiny fraction of what exists in the universe. If we were to take all the matter in a galaxy and spread it evenly across its volume, it would be so thinly spread that it could not be detected without sensitive instruments. The universe, on the grand scale, is a place where matter is rare and voids are normal. The emptiness is not random or chaotic. On the larger scales, the universe has structure. Galaxies form clusters, clusters form filaments, and in between these structures are enormous voids. These voids can span hundreds of millions of light years. Within them, there may be a few stray atoms per cubic meter, or even fewer. This is far emptier than the best vacuum humans can create in a laboratory. The universe is made mostly of these vast spaces. They are not filled with dark clouds or gases, but are near-perfect vacuums. The more we look, the more we realize that the regions containing stars, planets, and galaxies are rare islands within an ocean of nothing. Even within galaxies, space is mostly empty. The Sun, which seems enormous to us, is just one of hundreds of billions of stars in the Milky Way. Yet the distance to the nearest star, Proxima Centauri, is over 4 light-years away. 4 light-years is more than 37 trillion kilometers. Light travels fast, faster than anything we can move, yet it takes years to cross even the smallest gaps between stars. Within this distance, there is almost no matter. This emptiness surrounds us even in the neighborhood we know best. Planets circle stars, stars circle the galaxy, yet almost all the volume in between remains void. If we zoom out further, to the scale of the entire observable universe, emptiness becomes overwhelming. Galaxies themselves are tiny points of light in a cosmos that stretches for more than 90 billion light-years in diameter. Each galaxy is mostly empty space as well. Stars occupy a tiny fraction of a galaxy's volume, and planets are mere specks within that. The space between galaxies is even more empty, with particles separated by millions of kilometers. Our sense of fullness, our impression that the sky is crowded with stars, is a trick of perspective. Reality is dominated by absence. This emptiness has profound consequences for physics and the nature of reality. When matter is sparse, the effects of gravity weaken over distance. Light can travel freely for billions of years without hitting anything. Radio waves, cosmic rays, and particles all move through these voids nearly unimpeded. The vacuum of space is not just empty in a visual sense. It defines the rules for energy and motion, allowing the universe to expand and matter to interact across vast distances. The more we measure, the more we see that nothing is not just a lack of things, but an essential component of how the cosmos functions. The illusion of fullness comes from human experience. On Earth, almost every space is filled with air, dust, or water. We are used to contact and resistance, to things pressing against each other. Space offers none of this. In the emptiness of interstellar and intergalactic space, there is no air, no pressure, no molecules to obstruct movement. A spacecraft or a particle can drift for millions of kilometers with almost no interference. The void allows light from the earliest stars and galaxies to travel uninterrupted, carrying information across the universe. The silence and emptiness of space are real and measurable. Even when matter exists, it is spread thin. Gas clouds, which we see as bright nebulae in telescopes, are mostly empty. A cubic meter of nebula might contain only a few million atoms. Compare this with a breath of air on Earth, which contains trillions of molecules in the same space. Dust grains and cosmic rays are scattered sparsely across millions of kilometers. Stars, despite their brightness and size, occupy an almost invisible fraction of the universe's volume. Everywhere we look, the evidence points to the same conclusion. The universe is mostly nothing, a stage defined by the absence of matter. The idea that the universe is empty is not new, but modern astronomy has quantified it in ways that were once impossible. Surveys of galaxies, measurements of cosmic radiation, and simulations of cosmic structure all show that matter is sparse on large scales. Even in the densest regions of galaxy clusters, the space between stars is far emptier than anything we can produce on Earth. Observing the cosmos is like looking at a few fireflies scattered across an endless dark field. The darkness is far more vast than the light. Every telescope and every measurement reinforces the truth. The universe is almost entirely empty, with matter forming tiny islands in a sea of nothing. The emptiness is not uniform. The distribution of matter follows patterns formed by gravity. Filaments of galaxies stretch across hundreds of millions of light years, outlining shapes that resemble a web. Between these filaments lie voids, massive regions, where galaxies are almost absent. These cosmic voids are some of the largest structures in the universe, and they occupy most of the space. The more we study these voids, the more we realize that emptiness is not an absence of structure, but a defining feature of the universe. Space itself is mostly unoccupied, and this unoccupation shapes the evolution of galaxies and stars. The distances in space also challenge our perception of emptiness. A light year, the distance light travels in 1 year, is almost 10 trillion kilometers. Even the nearest star is more than 4 light years away. Our solar system, which seems large, is tiny compared to the gaps between stars. Planets occupy negligible volume. Even when galaxies cluster together, their interiors are overwhelmingly empty. The cosmic web shows us that matter prefers certain places, but even then, the emptiness dominates. Most of what exists is space itself, not the objects it contains. As we measure matter in the universe, the numbers are astonishing. Ordinary matter, protons, neutrons, electrons, makes up less than 1% of the total content of the cosmos. Everything we can see, touch, or measure directly is confined to this fraction. Stars, planets, gas clouds, and dust form a tiny contribution to the universe's overall energy. Everything else is empty space, dark matter, or dark energy. The vastness of the void is not a minor feature. It is the defining characteristic of the cosmos. From this perspective, the universe is 99.9% nothing, and the matter we notice is a tiny exception. In this context, the night sky can be seen differently. The points of light are reminders of islands of matter in a sea of emptiness. Each star is precious because it is rare. Each galaxy a tiny cluster amid billions of voids. The darkness between them is not absence in a simple sense, but a dominant presence. It defines how galaxies move, how light travels, and how structures form. The emptiness allows space to expand, allows forces to act over incredible distances, and creates the conditions for matter to exist at all. Without this nothingness, the universe would not be as it is. Even in our daily understanding, the scale of emptiness stretches our minds. Walking through a room, we feel filled space. A city street feels dense with matter. But in the universe, density is extreme. A single atom may be isolated over kilometers of void. The average density of matter in the universe is far lower than any earthly vacuum. The numbers are hard to imagine, but they are real and measurable. Emptiness is not a poetic idea. It is a scientific fact. From the smallest interstellar clouds to the largest cosmic voids, nothing dominates the volume of space. The sense of fullness is tied to perception. Human eyes see only the brightest objects. Telescopes reveal more, but even then, the majority of space remains dark. The light we detect travels through vast stretches of nothing, taking millions or billions of years to reach us. The cosmos is like a vast ocean where visible matter is a few floating islands. The emptiness is continuous, stretching beyond the limits of observation. In all directions, the space between stars, planets, and galaxies is overwhelmingly vast. The universe is not mostly full. It is mostly nothing. And understanding this gives us a new perspective on the cosmos and our place within it. Every object we see and touch, from the smallest pebble to the largest planet, is made of ordinary matter. Scientists call this baryonic matter. It is made up of protons, neutrons, and electrons. Protons and neutrons form the cores of atoms, and electrons move around these cores. Together, these tiny particles create the atoms that combine to form molecules. Molecules build rocks, water, air, and living creatures. The air we breathe, the ground we walk on, even our own bodies are composed of this ordinary matter. It is what we know, what we can measure directly, and what makes up the visible world around us. Despite its importance to life and the things we observe, ordinary matter is extremely rare in the universe as a whole. In fact, it accounts for only about 0.5% of the total energy in the cosmos. This number might seem small, but it is the fraction that forms everything we recognize. Stars, planets, dust clouds, and gas are included in this tiny percentage. All the galaxies, the clusters of galaxies, and the matter between them together make up far less than 1% of what the universe contains. Nearly all the rest is something we cannot see, something invisible yet influential. Dark matter and dark energy. Even when we look at the largest stars or the densest clouds, the quantity of ordinary matter remains minuscule on a cosmic scale. Consider a galaxy. It may contain hundreds of billions of stars. Each star contains enormous amounts of matter. Even then, the space between stars is so vast that the stars themselves occupy almost no volume. The same applies to planets and dust. They are tiny points within enormous spaces. If we could spread all the matter of the Milky Way evenly, it would be so thin that it would be nearly invisible, a ghostly trace across the vast emptiness. Ordinary matter is concentrated in small pockets, while the universe itself is overwhelmingly empty. Observations confirm this scarcity. Surveys of galaxies show that they cluster along filaments, leaving vast voids between them. Even within these clusters, the space between stars and planets remains mostly void. Measurements of the cosmic microwave background, the faint glow left over from the Big Bang, reveal the density and distribution of ordinary matter in the early universe. This radiation shows us a universe that was almost uniform, with small variations. These tiny variations grew into the structures we see today. They also demonstrate that ordinary matter has always been a small part of the cosmos, a fraction of the total energy that has always been dwarfed by the emptiness around it. The early universe was hot, dense, and filled with plasma, a mix of protons, neutrons, and electrons moving freely. In that state, ordinary matter was more uniformly spread. But as the universe expanded and cooled, matter began to clump under gravity. Tiny fluctuations in density grew over time, forming galaxies, stars, and clusters. Even with these structures, ordinary matter remained sparse. The empty spaces continued to dominate. We see the result in the night sky. Each galaxy is a small collection of matter surrounded by vast emptiness. Most of what exists in the universe is not stars or planets, but the voids between them. On a cosmic scale, ordinary matter behaves as islands in an ocean. Each particle, each atom, is a rare occurrence across the vastness of space. Intergalactic space is almost completely empty, with just a few stray atoms per cubic meter. Even in the densest clouds of gas, particles are far apart compared to any human scale. The density of ordinary matter is unimaginably low when measured against the volume it occupies. From a distance, galaxies are bright points, but the space they occupy is a tiny fraction of the overall universe. The voids surrounding them are so large that they dwarf the matter we can see. Cosmic microwave background measurements not only show the amount of ordinary matter, but also provide a map of where it existed in the early universe. Tiny temperature fluctuations in this radiation correspond to slightly denser regions that would eventually form galaxies and clusters. These maps tell a story of rarity and sparsity. Most of the volume of the universe was already empty, or nearly so, even when matter was forming. The observed structures are only small traces in an otherwise vast emptiness. Ordinary matter has always been and remains a minor player compared to the nothingness that stretches across the cosmos. Galaxy surveys provide further evidence. Observatories scan large regions of the sky, detecting millions of galaxies. The data show that galaxies are not evenly distributed. They follow a web-like pattern, creating long filaments and walls of matter. Between these filaments are enormous voids where few or no galaxies exist. Even within filaments, the gaps between stars are enormous. Observational science repeatedly confirms that ordinary matter is confined to tiny regions. The spaces between these regions dominate, reinforcing the idea that the universe is largely nothing. The structures we see are only the tip of an immense, mostly empty cosmic iceberg. The proportion of ordinary matter is small, not because there is little to count, but because the universe itself is so vast. A single star might contain the mass of 1,000,000 Earths, yet the volume of empty space around it is far larger. Galaxies contain billions of stars, but they are separated by distances so immense that they seem almost isolated. Ordinary matter clusters due to gravity, forming planets, stars, and galaxies. But even these clusters occupy a tiny fraction of the cosmos. The rest is dark matter, dark energy, or the void itself. This context helps us understand why, on the larger scale, matter is almost negligible. Even human bodies, though composed entirely of ordinary matter, are insignificant in the grand scheme. Each of us contains about 10 trillion cells, each with billions of atoms. That is immense on a personal scale. Yet compared to the universe, it is nothing. The atoms in a single human are a minuscule fraction of the total ordinary matter, which itself is only a tiny fraction of the universe. Our perception of fullness is misleading. We see density in our surroundings, but on cosmic scales, ordinary matter is sparse, rare, and far between. Gas clouds, dust, and plasma form another visible part of ordinary matter. Nebulae are bright and colorful in telescopes, yet even the densest clouds contain just a few million particles per cubic meter. In comparison, a breath of air contains trillions of molecules in the same volume. Dust grains are scattered across enormous spaces. Stars shine brightly, but the volume they occupy is a tiny fraction of the galaxy. The contrast between brightness and emptiness is striking. Matter exists, but it is isolated. The universe is defined not by what is present, but by what is absent. Ordinary matter is a tiny fraction in a sea of emptiness. From the earliest moments after the Big Bang to today, ordinary matter has been the visible and tangible part of the universe, yet it has never been the dominant part. Dark matter and dark energy control the dynamics of cosmic expansion, galaxy formation, and large-scale structure. Ordinary matter forms stars, planets, and life, but these are rare. Observational evidence from the cosmic microwave background to galaxy surveys confirms the same truth repeatedly. Most of the universe is empty. What we see, what we can touch, what we can measure directly, is only a small exception in a vast cosmic void. Even when we observe the most familiar stars, the matter they contain is still a small fraction of their volume. The light we detect from distant galaxies comes from ordinary matter, but this light travels through enormous stretches of empty space. Intervening space is nearly void. Dust, gas, and plasma are sparse, often separated by millions of kilometers. Ordinary matter exists as islands, while the spaces between these islands define the true nature of the universe. Understanding this rarity is crucial for grasping the scale and composition of everything around us. Ordinary matter, though tangible and essential for life, is ultimately a small part of the cosmic picture. It is concentrated in stars, planets, gas, and dust, yet these concentrations are exceptions. The emptiness surrounding them dominates. This small fraction is what we detect, study, and understand directly. Beyond it lies an overwhelming majority of the universe, composed of dark matter, dark energy, and nearly perfect vacuum. Ordinary matter is precious in its rarity, yet it is not what fills the universe. The universe is mostly nothing, and this truth shapes everything we observe and measure. When we step back from individual stars and galaxies, the universe begins to reveal its grand pattern. Galaxies are not scattered randomly across space. They form clusters, groups of galaxies bound together by gravity. These clusters connect in long, thin structures called filaments, stretching across hundreds of millions of light years. Between these filaments lie immense regions nearly devoid of matter, known as cosmic voids. These voids are the largest structures by volume in the universe. Though they contain some stray atoms or occasional dwarf galaxies, their emptiness dominates. Vast stretches of space exist where a single atom may be separated from another by kilometers or more, and light passes through without encountering anything significant. The filaments themselves appear as chains of galaxies and clusters, outlining a web-like structure across the cosmos. When we look at images from deep surveys of the universe, the bright spots show where matter has gathered. Between these bright threads, the darkness is almost absolute. The voids are vast compared to the clusters and filaments, stretching for tens to hundreds of millions of light years. If a human mind tries to picture these scales, it is nearly impossible. Even light, the fastest thing in the universe, takes millions of years to cross these empty regions. The distances make the few islands of matter seem even smaller, and the emptiness more overwhelming. Inside a void, the physical conditions are unlike anything we experience on Earth. Space is a near-perfect vacuum. Particles are extremely sparse. In the most extreme emptiness, there may be only 1 atom per cubic meter. For comparison, the best laboratory vacuums on Earth still contain trillions of particles in the same space. Temperature in these regions is low, close to the cosmic microwave background of about 3 degrees above absolute zero. There is almost no pressure, almost no collisions between particles. It is a quiet, still expanse where energy moves freely and matter is a rare visitor. The void is a natural laboratory, demonstrating what space is like when it is largely untouched by stars and galaxies. The voids are not uniform in size or density. Some are smaller, spanning tens of millions of light years, while others are enormous, stretching over hundreds of millions. Within a void, small filaments of matter may thread through, forming rare, isolated galaxies or gas clouds. These sparse features are exceptions in a sea of emptiness. Even within filaments, the density is low compared to what we experience on Earth. Stars within galaxies are close together, relative to the emptiness outside, yet the empty space between galaxies and clusters is far greater. The majority of the universe's volume is contained within these voids. They shape the way gravity works on cosmic scales and influence the motion of galaxies over millions of light years. When we measure the distribution of matter across the universe, the contrast between voids and filaments becomes clear. Surveys of millions of galaxies map their positions and reveal the cosmic web. The voids occupy most of the space, while the filaments and clusters hold the matter that we can detect. The galaxies appear as bright threads against the dark background, but the darkness is far more abundant. Even massive galaxy clusters, dense compared to the surrounding voids, occupy only a tiny fraction of the total volume. Emptiness dominates by sheer scale, not just by absence of light. The universe is a vast expanse where nothing is the norm, and matter is the exception. Distances in voids are hard to imagine. A light year is almost 10 trillion kilometers. Across a void, spanning 100 million light years, light travels through space for 100 million years, passing almost nothing. The time and distance emphasize the rarity of matter. Particles in the void may drift for millions of years without encountering another particle. Collisions are extraordinary events, not commonplace. Photons, or particles of light, travel freely, carrying information across unimaginable distances. The emptiness defines the journey of light, the spread of energy, and the interactions that occur within the cosmos. Even within voids, some phenomena hint at the occasional presence of matter. A small galaxy may drift slowly through a void, containing billions of stars, yet it is isolated. Gas clouds, remnants of past interactions, float sparsely, almost invisible. Cosmic rays and neutrinos pass through the emptiness without hindrance. The void is not entirely devoid of influence. Gravity still shapes the motion of galaxies, and dark matter, invisible yet present, threads through these regions. Still, the ordinary matter, the stars, dust, and gas, is vanishingly rare. The void is a place where emptiness truly dominates, a stage set for the few pockets of matter that inhabit it. The visual experience of voids can be imagined from large-scale surveys. When astronomers map the positions of galaxies, the voids are the dark spaces between clusters. These voids are not empty in a poetic sense. They are real, measurable, and continuous. The emptiness stretches beyond what we can see. If a spacecraft could travel through a void at the speed of light, it would take millions of years to cross the distances between filaments. Within this vast nothingness, the few atoms that exist are spread across enormous expanses. Even when we see bright galaxies at the edges of voids, they are rare exceptions in a dominant darkness. Voids also influence the shape and motion of matter. Galaxies at the edges of voids tend to move away from the empty space drawn toward denser filaments by gravity. The voids expand as the universe grows, making the emptiness even more pronounced over time. Cosmic expansion stretches space, enlarging the voids and separating clusters and filaments. Matter collects along the threads, while the spaces in between grow. The universe evolves in a way that reinforces emptiness. What we observe today is the result of billions of years of expansion, clumping, and gravitational shaping. The empty regions are not passive. They define the cosmic architecture. Looking across a void, we imagine distances that dwarf human comprehension. Even a single particle may travel for millions of kilometers without meeting another. Light may pass uninterrupted for millions of years. The scale of emptiness makes the few objects we detect remarkable. Each galaxy, each star, each atom is a point of exception in a vast expanse. The cosmic void is a demonstration of how the universe is mostly nothing, where matter is concentrated only in islands connected by rare threads. The experience of scale, though imagined, helps us grasp the overwhelming dominance of emptiness. The physical conditions in voids also shape the universe's behavior. The low density reduces collisions, allowing gravity and dark matter to guide the motion of galaxies. Light moves freely, cosmic expansion progresses, and energy travels without obstruction. Even as the universe grows, the voids remain largely unchanged in their nature. They are a constant reminder that what we see, galaxies, stars, planets, is a tiny fraction of what exists. The empty space is the majority. The universe is constructed not just of matter, but of the emptiness that defines the distances and motions of all matter. Even small filaments of gas or dwarf galaxies in voids are rare features. They show that matter can exist, but only in small amounts. The voids are continuous and dominant, stretching in all directions. They occupy the volume that dwarfs clusters and filaments. Cosmic surveys, the mapping of millions of galaxies, and simulations of structure all point to the same fact. The majority of space is empty. This emptiness is measurable, observable, and central to understanding the universe. It is not just background. It is the foundation of cosmic structure. Void regions highlight the contrast between matter and space. While clusters of galaxies concentrate ordinary matter, the voids reveal its absence. Temperature, pressure, and particle density are all extremely low. Particles drift almost without interaction. Gravity operates over long distances, but ordinary matter remains rare. Light travels for millions of years across these voids, experiencing almost no obstacles. The universe, on its larger scales, is a network of matter framed by overwhelming emptiness. The voids dominate by volume, demonstrating the true meaning of mostly nothing. The voids show us the scale and scope of emptiness. Filaments, clusters, and galaxies are islands in a sea of space. Even where matter exists, it occupies a tiny fraction of the universe. The vast emptiness of voids, stretching across millions of light years, defines the structure and evolution of the cosmos. The spaces between objects are not minor or incidental. They are the majority. Understanding the voids helps us comprehend how small the fraction of matter is, and how overwhelming the nothingness truly is. The universe, in volume and in scale, is defined more by what is absent than what is present. The universe is mostly empty, yet there is more to its composition than ordinary matter. Invisible, unseen, and mysterious, dark matter makes up a much larger portion of the cosmos. It cannot be seen with our eyes or measured directly by instruments that detect light. Unlike stars, gas, or dust, dark matter does not emit or absorb light. We cannot touch it, hold it, or feel it in any conventional way. Its presence is known only through its effect on gravity, the way it pulls on galaxies, clusters, and other visible matter. Without dark matter, the universe would look very different, and the structures we observe today might never have formed. Scientists estimate that dark matter makes up roughly 27% of the universe's total energy and mass. Compared with ordinary matter, which forms only a tiny fraction, dark matter dominates the gravitational landscape of space. Even though we cannot see it, it provides the invisible scaffolding for galaxies and clusters. The shapes of galaxies, their rotation speeds, and the motion of clusters all point to the unseen weight of dark matter. Observations show that without this invisible mass, galaxies would fly apart, unable to hold themselves together. It is the hidden framework that shapes the cosmos. Despite its gravitational influence, dark matter does not fill space in a dense way. Much of the universe remains empty, just as with ordinary matter. Dark matter clusters around galaxies and filaments, forming halos that extend far beyond the visible edges of stars. Between these halos, the space remains largely empty. The majority of cosmic volume, in voids and across vast distances, is still dominated by nothingness. Dark matter does not create a solid or tangible presence. It interacts gravitationally, but otherwise leaves the vast voids untouched. The universe's emptiness persists even with this invisible component. Galaxies themselves owe much of their existence to dark matter. When the universe was young, small fluctuations in density occurred in ordinary and dark matter together. Gravity pulled matter into denser regions, where ordinary matter collected to form stars. Dark matter created deep gravitational wells, anchoring these regions and preventing them from dispersing. Without dark matter, galaxies might not have formed at all. Its presence guided the assembly of cosmic structures, helping matter clump and organize, yet it did not fill the spaces between. The majority of the universe remained, and still remains, vast and empty. Dark matter halos extend far beyond the luminous parts of galaxies. While stars and gas occupy the inner regions, dark matter surrounds them in a diffuse, invisible sphere. These halos contain more mass than the visible matter inside galaxies, but their density is extremely low. Across the cosmic web, filaments of dark matter provide the skeleton along which galaxies assemble. Simulations of the universe show these threads clearly, tracing the paths of ordinary matter and revealing the hidden architecture of the cosmos. Between the threads, emptiness dominates, punctuated only by rare concentrations of stars or galaxies. Even though dark matter shapes cosmic structure, it does not make the universe feel full. The spaces between filaments, clusters, and halos are still overwhelmingly void. In these regions, ordinary matter is sparse, and dark matter density is lower. Gravity from distant structures may influence the motion of galaxies, but the space itself remains mostly empty. Light travels through these regions largely unhindered. The combination of visible matter, dark matter, and empty space creates a universe in which the majority of volume is still dominated by nothingness. The invisible mass supports structure without filling the cosmos. Dark matter also affects galaxy motion in measurable ways. Observations of rotation curves, the speed at which stars orbit the center of galaxies, show that stars move faster than they would if only visible matter existed. The additional gravitational pull comes from dark matter, unseen yet undeniable. Galaxy clusters also show effects of dark matter through gravitational lensing, bending light from distant objects. These phenomena reveal the presence of mass we cannot directly detect. Even with these influences, the actual volume occupied by dark matter remains extremely low compared to the total volume of space. It shapes the universe without crowding it. Large-scale simulations help scientists understand dark matter's role in cosmic structure. When computer models include dark matter, filaments, clusters, and voids form in ways that match observations. Without dark matter, galaxies would be smaller, fewer, and more irregular. Dark matter guides ordinary matter, but it does not remove the dominance of emptiness. The vast voids that stretch across hundreds of millions of light years remain mostly void, punctuated by rare filaments or clusters. Even in a universe with 27% dark matter, emptiness still accounts for most of the volume. Nothingness is still the overwhelming majority. Dark matter interacts only through gravity, not electromagnetic forces. This explains why it does not glow, reflect light, or create pressure. It can pass through ordinary matter without friction or collision. Even if a planet or a star passes through a dark matter halo, nothing visible occurs. The effect is subtle yet measurable on cosmic scales. The gravitational influence of dark matter organizes clusters of galaxies and guides the formation of cosmic structures. Despite its unseen weight, dark matter leaves most space unaffected, preserving the emptiness that dominates the universe. In the vast cosmic web, dark matter creates invisible bridges connecting galaxies and clusters. It forms halos around galaxies, filamentary threads across space, and pockets within clusters. These structures contain the gravitational pull necessary for cosmic evolution. Yet the spaces between these concentrations are mostly empty. A photon traveling across the universe passes through vast stretches of nothing, interrupted only occasionally by matter clumps. Even the influence of dark matter is diffuse, spread over enormous distances. The voids between halos and filaments remain, and within these voids, emptiness continues to rule. Even as dark matter shapes galaxies, it does not eliminate cosmic voids. The largest, voids, hundreds of millions of light years across, remain largely free of ordinary and dark matter. Only a few atoms, stray particles, or faint dwarf galaxies reside within them. Gravity from distant filaments and clusters may influence these regions, but the overall density remains extremely low. Emptiness persists as the dominant feature of the cosmos. The universe, as we observe it today, is structured by dark matter, yet defined by the overwhelming absence of mass in most of its volume. The unseen weight of dark matter gives the universe its framework. Galaxies gather along its invisible threads, clusters form in its gravitational wells, and cosmic filaments trace the architecture of space. Without it, the large-scale structure would be fragile or disorganized. Yet the emptiness between these structures is not reduced. Vast voids continue to span enormous distances, stretching across billions of light years. Dark matter provides shape and stability without filling space. The universe remains, in the truest sense, mostly nothing, despite the invisible presence guiding its form. Even isolated galaxies owe their motion to dark matter. Satellites orbit their host galaxies under the pull of unseen halos. Clusters of galaxies move through space, influenced by the mass of dark matter distributed around them. These effects are measurable and predictable, yet they leave enormous gaps untouched. Between halos, voids dominate. The contrast between the dense cores of matter and the vast emptiness surrounding them is extreme. Dark matter shapes the universe, yet it does not challenge the emptiness that defines its volume. The presence of dark matter helps explain why ordinary matter appears clumped, while the universe remains mostly empty. Gravity from dark matter draws ordinary matter into stars, galaxies, and clusters. Between these clumps, the spaces are enormous, and the density is incredibly low. Even with this invisible mass, the universe's volume is dominated by nothing. Dark matter is essential for structure, but it does not reduce emptiness. The cosmos, in both matter and space, shows a clear truth. Even with nearly a third of its energy as invisible mass, the universe is still overwhelmingly nothing. It is a landscape of absence punctuated by rare islands of matter. Alongside the emptiness of space and the invisible weight of dark matter, the universe contains another, even more mysterious component. This is dark energy. It is not matter in any form that we can touch or see. It does not cluster like stars or gas, and it does not form halos around galaxies. Instead, it is a property of space itself, a force or energy that drives the expansion of the universe. Dark energy is everywhere, permeating all of space, pushing it outward. It is the reason the universe continues to grow, stretching the distances between galaxies, clusters, and filaments. Without it, cosmic expansion would slow down over time, and the universe would look very different. Dark energy makes up the largest portion of the universe, roughly 68% of its total energy. Ordinary matter, which we can see and touch, is less than 1%, and dark matter accounts for about 27%. This makes dark energy the dominant component of the cosmos. It is invisible and intangible, yet it determines how space behaves on the largest scales. Unlike gravity, which pulls matter together, dark energy drives space itself apart. It acts uniformly, affecting all regions, whether dense with galaxies or nearly empty. The more we measure, the more we realize that empty space is not just empty. It is active, stretching under the influence of dark energy. The effect of dark energy is to stretch space itself. This stretching is not like wind blowing objects apart. It is space expanding between objects, increasing the distances without the objects themselves moving locally. Galaxies are carried away from each other as the fabric of space grows. Light traveling across the universe must traverse this stretching space, which lengthens its journey. Over billions of years, the expansion driven by dark energy has increased the size of the universe many times over. This expansion makes the emptiness between galaxies, clusters and filaments grow continuously. Space is not static. It is a dynamic, stretching nothingness, becoming ever more vast. In the past, the universe expanded more slowly. Gravity from ordinary and dark matter worked to slow the growth of space. Galaxies were drawn together, clusters formed, and filaments became more pronounced. But roughly 6 billion years ago, dark energy began to dominate. Its effect overcame gravity on large scales, causing the expansion to accelerate. Today, galaxies are moving away from each other faster and faster. The observable universe is growing, and with it, the spaces between objects expand at an increasing rate. The cosmos is becoming emptier, not because matter is vanishing, but because the volume in which matter exists grows faster than matter can fill it. Even though dark energy is invisible, we can observe its effects. Measurements of distant supernovae, the cosmic microwave background, and the distribution of galaxies all point to accelerated expansion. These observations show that the universe will continue to grow larger over time, increasing the separation between galaxies. Clusters that are near each other today may become isolated over billions of years, with light from one cluster no longer able to reach another. The volume of empty space will expand faster than the addition of new matter. Dark energy ensures that emptiness becomes the dominant feature of the cosmos for the foreseeable future. As the universe expands under dark energy, the density of matter decreases. Even though galaxies, stars, and planets continue to exist, they occupy a smaller fraction of the growing universe. Ordinary matter, already rare, becomes even more diluted. Dark matter halos stretch along with space, but the voids grow larger, making the vast stretches between objects more pronounced. Over time, the universe will become a place where galaxies appear as isolated islands surrounded by emptiness. The acceleration caused by dark energy emphasizes the role of nothingness. Most of the volume of the universe is not occupied by matter. It is filled with expanding space. Dark energy also changes the way we perceive cosmic distances. A galaxy that is visible today may eventually recede faster than light can travel toward us. The stretching of space prevents its light from reaching Earth. In this sense, dark energy extends emptiness into the future, making regions of the universe inaccessible. The observable universe may shrink in practical terms, even as space continues to expand overall. What was once near becomes unreachable, leaving behind an even emptier cosmos. Dark energy drives this process, ensuring that the dominance of nothingness grows with time. The accelerating expansion also affects the cosmic web. Filaments of galaxies, the clusters along them, and the sparse gas between structures are all carried apart. The thin connections that link clusters may be stretched to the point that galaxies become effectively isolated from one another. The voids between filaments continue to grow, becoming larger relative to the matter within them. The universe evolves into a state where concentrations of matter remain, but the space they inhabit expands faster than they can occupy. Dark energy does not remove galaxies, but it enlarges the emptiness around them, defining the cosmos in terms of absence. Over billions of years, the influence of dark energy will become more extreme. Local groups of galaxies, held together by gravity, may remain bound, but distant clusters will recede beyond view. The expansion stretches the distances between them at an accelerating pace. Light emitted from these galaxies will never reach observers elsewhere. In this future, the universe will appear as scattered islands of matter floating in a vast ocean of nothing. Even the strongest gravitationally bound systems will exist within a growing emptiness. Dark energy dictates the pace at which space itself increases, amplifying the dominance of nothingness. The measurable properties of dark energy suggest it is uniform and constant. It does not cluster. It does not vary significantly across space. This uniformity means that all regions of the universe, dense or empty, experience the same stretching effect. The volume of empty space grows steadily, while the matter within remains confined. Ordinary and dark matter, though essential for the formation of galaxies and stars, are increasingly diluted by the accelerating expansion. Dark energy ensures that empty space will continue to dominate the cosmic landscape, reinforcing the 99.9% emptiness of the universe. Dark energy also provides context for why the universe feels so empty, even in areas filled with matter. While stars, galaxies, and clusters are visible, the expansion driven by dark energy stretches the space around them. The voids grow, the distances increase, and the observable universe appears sparse. Light from distant objects takes longer to reach us, and the density of matter per volume decreases. The universe is not static. It is a dynamic, expanding fabric in which nothingness grows steadily. The emptiness we observe today will become even more extreme in the future. Even the largest structures, like superclusters and filaments, are subject to the influence of dark energy. The acceleration separates them further, stretching the connections that link clusters. Some galaxies may drift away beyond observation entirely. The cosmic web remains, but the voids within and between filaments expand. Space itself becomes more dominant than the matter it contains. In this way, dark energy shapes not only the expansion of the universe, but also the perception of emptiness, making the vast nothingness the defining feature of the cosmos. In combination with ordinary matter and dark matter, dark energy completes the cosmic picture. Ordinary matter forms stars, planets, and galaxies. Dark matter provides the gravitational scaffolding for these structures. Dark energy drives the growth of empty space, enlarging the distances and emphasizing the rarity of matter. Together, they create a universe in which matter is rare and emptiness is overwhelming. Even though dark energy is invisible, it is the force that ensures nothingness dominates the cosmos, and that the universe will remain mostly empty for billions of years to come. The continuous stretching caused by dark energy also affects the future interaction of galaxies. Collisions between distant galaxies will become less frequent. Groups of galaxies that are not gravitationally bound will drift apart, leaving behind regions of isolation. The more the universe expands, the more isolated matter becomes, and the more space is defined by emptiness. Even though matter exists, the effect of dark energy ensures that the universe is increasingly empty on the largest scales. The growth of nothingness is ongoing, dynamic, and unavoidable. Dark energy highlights a cosmic truth. The universe is defined by its emptiness. Matter, both ordinary and dark, occupies small regions, forming islands within a vast expanse. The remaining space, shaped and stretched by dark energy, is empty. This nothingness is not passive. It grows, accelerates, and dominates. The universe, in energy and volume, is primarily nothing. Dark energy ensures that as time passes, the distances grow, the voids expand, and the small fraction of matter becomes ever less significant. Emptiness is not just present. It is the defining property of the cosmos. When we speak of emptiness in the universe, it is tempting to imagine a space with absolutely nothing, a perfect void. Yet, on the smallest scales, the universe behaves in ways that defy ordinary intuition. Even what we call empty space is not truly empty. In quantum physics, the vacuum is a seething, restless arena of activity. The vacuum is filled with what scientists call zero-point energy, the lowest possible energy that still exists even in the absence of matter or radiation. It is a background hum that pervades all of space, invisible to our eyes but present everywhere. The emptiness between stars and galaxies is not a simple absence. It is a quantum field alive with possibilities. At the heart of this concept are virtual particles. These particles appear and disappear constantly, materializing from the vacuum for a brief moment before vanishing. They are not ordinary matter, and they cannot be captured or observed directly, yet their effects are measurable. Virtual particles influence the forces between charged particles, contribute to the energy levels of atoms, and affect fundamental interactions across the universe. They are a fleeting presence, ghostly ripples in the fabric of space. Even when a region seems entirely devoid of matter, these ephemeral particles remind us that the vacuum has structure, that nothingness at the quantum level is never complete. Zero-point energy is a measure of the intrinsic fluctuations of the quantum vacuum. Even at absolute zero temperature, when all thermal motion ceases, space still vibrates with this energy. The vacuum is not calm. It is filled with tiny oscillations that cannot be removed. These oscillations contribute to the background energy of the universe. On large scales, this energy may connect to the phenomenon we call dark energy. Some theories suggest that the energy of empty space drives the accelerated expansion of the cosmos. While ordinary matter is rare and dark matter is invisible, the vacuum itself has a subtle, pervasive presence that influences cosmic evolution. The concept of vacuum energy also explains certain observable effects in the laboratory. In the Casimir effect, two metal plates placed very close together experience a tiny force pushing them together, caused by changes in the vacuum energy between them. This is a direct demonstration that even seemingly empty space exerts influence. Photons, virtual particles, and quantum fluctuations all contribute to measurable effects that defy the common notion of emptiness. Space is not an empty container waiting to be filled. It is an active field, a stage on which the universe operates even when no matter is present. The nothing of human imagination is far from the nothing of physics. In cosmology, the quantum vacuum is more than a curiosity. It underlies fundamental questions about the origin and fate of the universe. The energy contained in the vacuum may have shaped the inflationary period shortly after the Big Bang, a time when space expanded exponentially. The same properties may contribute to dark energy today, stretching the cosmos and increasing the distance between galaxies. The interplay between quantum vacuum and cosmic expansion links the smallest scales to the largest, connecting subatomic fluctuations with the evolution of the entire universe. What seems empty at one scale is dynamic at another. The human intuition of nothingness struggles to reconcile with this reality. We tend to think of empty space as a void, a lack of substance, a silent backdrop, yet science shows us that the vacuum is a restless sea. Every cubic centimeter of empty space contains virtual particles appearing and disappearing, energy fluctuations, and the underlying quantum fields that define reality. Even in the darkness between galaxies, the quantum vacuum is vibrant, a stage for forces and phenomena that shape matter, light, and energy. Nothing is never truly silent. It is full of subtle activity that escapes ordinary perception. Quantum fluctuations can influence the formation of matter in the early universe. During cosmic inflation, tiny differences in energy density within the vacuum grew over time. These small variations eventually became the seeds of galaxies and clusters. ordinary matter collected along the slight over-densities, guided by the gravitational pull shaped by dark matter. The patterns of the cosmic web may trace their origin, in part, to the restless activity of the quantum vacuum. Even the emptiness that dominates cosmic volume carries within it the blueprint for the structures we observe today. The vacuum also challenges our understanding of energy in space. While ordinary matter can be counted, measured, and observed, vacuum energy exists without any physical substance. It is energy inherent to space itself. This distinction sets the vacuum apart from the empty containers of everyday experience. Light, particles, and forces interact with the vacuum, demonstrating that nothing has properties. The emptiness between stars is thus a medium, subtle and invisible, but significant. The quantum vacuum makes the universe more complex and more alive than our intuition suggests, even in regions devoid of ordinary matter. The presence of vacuum energy highlights a surprising fact. Emptiness can have effects. It can exert pressure, influence gravity, and contribute to the expansion of space. Dark energy, though mysterious, may be the large-scale manifestation of these quantum effects. Ordinary matter occupies islands in space. Dark matter provides unseen weight, and the vacuum itself is a dynamic background, filled with energy and activity. The universe is not composed solely of objects separated by emptiness. The vacuum participates in cosmic evolution, giving structure and motion even where matter is scarce. Nothingness is active, not passive. Even though the vacuum is everywhere, it is often overlooked because it doesn't glow, reflect light, or form visible structures. Yet its influence is profound. It affects the behavior of particles, the forces that bind atoms, and the large-scale expansion of the cosmos. The quantum vacuum is a subtle actor in the drama of the universe. It is not a simple emptiness, but a sea of fluctuations, energy, and invisible activity. The void between galaxies is filled with this quantum structure, reminding us that even the most empty regions of space are alive with the rules and energies that govern reality. In this way, the quantum vacuum connects the micro and macro scales. Subatomic processes ripple into larger phenomena. Tiny, fleeting virtual particles help define the properties of matter, influence atomic structure, and contribute to forces we can measure. On cosmic scales, the same underlying fields may contribute to the stretching of space through dark energy. The smallest elements of reality and the vastest structures of the universe are intertwined through the quantum vacuum. Even in emptiness, there is a hidden order, a quiet energy that underlies the apparent nothingness. Our understanding of nothingness is therefore incomplete if we rely on intuition alone. What seems empty, what seems devoid of substance, is actually rich with energy and subtle activity. The quantum vacuum demonstrates that the universe's emptiness is layered. Visible matter occupies tiny fractions, dark matter shapes invisible structures, and the vacuum hums with energy. These layers of existence reinforce the sense that the universe is mostly nothing, yet they also show that nothing is not inert. Even the void is alive with the forces that shape galaxies, guide light, and sustain the cosmos. The quantum vacuum illustrates that emptiness has a depth that challenges our imagination. It is not a simple absence, but a background of restless energy. It is everywhere, filling the vast voids between stars and galaxies, influencing the formation of structures, and possibly driving the expansion of the universe through dark energy. Human intuition may think of nothing as blank or silent. Yet, science shows that the vacuum is active, complex, and essential. The universe is overwhelmingly empty, Yet even this emptiness is alive, forming a bridge between the smallest and largest scales, between particles and cosmic voids, between the ordinary and the extraordinary. The universe carries with it a faint, ancient whisper, a signal from a time when everything was young. This is the cosmic microwave background, or CMB, the fossil light of creation. It is the remnant radiation from the early universe, a glow left over from the time when the cosmos was hot, dense, and full of energy. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Before this moment, photons, particles of light, could not travel freely. They scattered endlessly off charged particles trapped in a dense opaque fog. When atoms formed, the photons were released, and space became transparent. These photons have been traveling ever since, across the vast emptiness, stretching and cooling as the universe expands. Today, they fill all of space, forming a nearly uniform background with a temperature of just under 3 degrees above absolute zero. The CMB is remarkably uniform, yet it carries tiny fluctuations. These fluctuations indicate small differences in density in the early universe, where some regions were slightly more packed with matter than others. These overdense and underdense regions served as the seeds for the galaxies, clusters, and filaments we observe today. The pattern of the CMB provides a snapshot of the universe when it was only a fraction of a million years old. The light has traveled across billions of years of nearly empty space, showing that even in the past, the universe was dominated by what we would consider emptiness. Matter, then as now, occupied only a tiny fraction of the total volume. Photons from the CMB have crossed unimaginable distances. They have moved through regions that are almost entirely void, passing far from stars, galaxies, and clusters. Collisions are rare, and interactions are minimal. These photons have survived the stretching of space itself, traveling billions of years to reach our instruments. The vast majority of the universe remains empty along their paths. Even the faint signal we detect today comes from a universe that has expanded enormously since those first photons escaped. The journey of this light highlights the sparsity of matter, emphasizing how small a portion of space is actually occupied by detectable objects. The CMB also illustrates the scale of emptiness. The photons we detect now are only slightly affected by the matter they encounter, yet they have traversed the entire observable universe. The vast regions between clusters, filaments, and galaxies have offered little resistance, nearly perfect vacuum for light to cross. The cosmic background radiation is, in effect, a map of the empty space that dominates the universe. The fluctuations in the CMB are subtle, demonstrating that the early universe was not perfectly uniform, but the differences are small. Even then, matter was rare, and space was largely empty, hinting at the vast nothingness that defines the cosmos. Modern instruments capture the CMB in remarkable detail. Satellites such as COBE, WMAP, and Planck have mapped the sky, revealing the tiny temperature variations across the cosmic background. Each variation corresponds to a slight difference in the density of matter in the early universe. The regions that were slightly denser became the first clumps of matter, guiding the formation of galaxies. Between these regions, photons traveled unimpeded. These observations confirm that most of the universe, both then and now, is empty. The light itself tells the story of a cosmos where matter is rare and nothingness is the dominant component. Even the photons that now reach Earth have spent billions of years in nearly perfect vacuum. The distances, they have traveled dwarf our experience of space. A single photon from the CMB may have crossed hundreds of millions of light years before encountering a galaxy or particle. This reinforces the sense of scale and sparsity. Stars and galaxies appear as bright points in our telescopes, but between them lies enormous emptiness. The CMB acts as a cosmic mirror, reflecting the quiet vastness of space and showing that matter, though essential, occupies only a minuscule fraction of the total volume. The fossil light also reveals how little matter existed relative to space, even in the early universe. While the density was higher than it is today, the universe was dominated by energy, radiation, and the vast spaces between particles. Ordinary matter made up only a tiny fraction of the total. Dark matter was present, forming invisible scaffolds, but even with its influence, the universe remained mostly empty. The CMB captures this early emptiness, providing direct evidence that the pattern of sparsity was established almost immediately after the universe became transparent. The vastness of nothingness has been a defining feature from the very beginning. As these photons move through space, they continue to experience the effects of cosmic expansion. The wavelength of each photon stretches, shifting from visible and infrared light in the early universe to microwave wavelengths today. This stretching is a reminder that space itself grows, increasing the distances between objects and emphasizing the rarity of matter. The background radiation that fills every direction we look is a persistent witness to emptiness. It shows that, across billions of light years, space remains largely empty, with galaxies and clusters acting as small, bright exceptions in an ocean of darkness. The CMB also allows scientists to measure the overall composition of the universe. By analyzing the tiny variations in temperature and polarization, cosmologists can determine the relative amounts of ordinary matter, dark matter, and dark energy. These measurements confirm that ordinary matter constitutes less than 1% of the total energy density, while dark matter and dark energy dominate. This reinforces the conclusion that matter, visible or invisible, occupies a tiny portion of space. Most of the cosmos is, and always has been, empty in the sense that it contains no particles or objects that interact with light in conventional ways. Even today, when we observe galaxies, stars, and nebulae, they are islands in a vast sea. The CMB reminds us that this sparsity is not a recent development, but a fundamental feature of the universe. Photons have traveled across near total emptiness for the entirety of cosmic history, witnessing the formation and evolution of galaxies while passing mostly through nothing. The emptiness is not an accident of scale or time. It is a consistent and measurable property of the cosmos. The fossil light of the universe tells us that emptiness is not only widespread, but persistent. The CMB also provides perspective on the human experience of space. The sky may appear dense with stars to the naked eye, yet the observable universe is dominated by vast voids. The light from the cosmic background has traversed these voids, reinforcing the contrast between dense regions and empty ones. Even where clusters of galaxies exist, the empty spaces between them are enormous. Light from distant clusters may take millions of years to reach us, highlighting the sparsity of matter on the larger scales. The CMB confirms that emptiness is the dominant state of the universe, shaping its history and evolution. The cosmic microwave background is a quiet testimony to the scale of nothingness. It demonstrates that even shortly after the universe became transparent, matter occupied only a fraction of space. As photons travel across billions of years and billions of light years of near vacuum, they remind us that the universe is vast, sparse, and overwhelmingly empty. The fossil light is evidence of the emptiness that defines the cosmos, showing that while matter exists in islands, it is the empty space between that dominates, both in volume and in experience. The universe is, and always has been, mostly nothing. Among the emptiness of the cosmos, black holes stand as remarkable concentrations of matter. They form where gravity has compressed material to an extreme degree, creating a region from which nothing, not even light, can escape. Despite their dramatic presence, black holes are incredibly rare on a cosmic scale. A single stellar black hole forms from the collapse of a massive star, and even supermassive black holes, residing at the centers of galaxies, occupy only a tiny fraction of the universe's total volume. The vast majority of space remains untouched, silent and empty, stretching between stars, galaxies, and clusters. Black holes are islands of intense gravity in a sea of nothingness. Black holes vary in size from those a few times more massive than the Sun to giants millions or billions of times more massive. Supermassive black holes sit at the heart of most large galaxies, influencing the motion of stars and gas nearby. Their gravitational pull organizes matter, guiding the formation of disks, jets, and the dynamics of galactic centers. Despite their power, the volume they occupy is negligible. The event horizon, the boundary beyond which nothing can escape, is tiny compared to the distances between stars or galaxies. Black holes concentrate matter, yet the universe around them remains overwhelmingly empty. Their formation is a testament to the extremes of matter in a mostly empty universe. Stars collapse under their own gravity, accumulating density until a singularity forms at the core, hidden behind an event horizon. In the centers of galaxies, repeated accretion of matter and merging of smaller black holes build supermassive versions. These structures anchor galaxies and affect their evolution. Yet they do not fill space. They are points of intense gravity surrounded by vast voids. Even in the densest regions of a galaxy, most of the volume is still made of empty space between stars. The contrast between black holes and their surroundings emphasizes the scale of nothingness. Observationally, black holes reveal their presence indirectly. X-rays and other high-energy radiation emerge as matter spirals into the black hole, forming an accretion disk. Gravitational lensing, where the black hole bends light from background objects, offers another way to detect them. These methods show that while black holes influence their immediate surroundings, they occupy extremely small volumes relative to the cosmos. Their gravitational fields extend far, shaping nearby stars and gas. But the universe at large remains sparsely populated with matter. The emptiness of space dwarfs the localized presence of these exotic objects. Even supermassive black holes weighing billions of solar masses occupy a minuscule fraction of cosmic volume. A galaxy may host a central black hole, yet the vast stretches between galaxies are entirely free of such concentrations. The influence of gravity diminishes with distance, leaving intergalactic space nearly untouched. Light travels unimpeded through these voids, covering millions of light years between dense structures. The universe is dominated by empty regions punctuated by isolated islands of concentrated matter, of which black holes are the most extreme examples. They form an exceptional, almost symbolic contrast to the pervasive nothingness. Black holes also affect the dynamics of galaxies in subtle ways. Stellar orbits near the center respond to the central mass, gas flows adjust, and energetic outflows sculpt the surrounding medium. These effects are dramatic in scale relative to a star or a cluster, yet they do not alter the broader emptiness beyond the galaxy. The intergalactic medium, the diffuse gas, between clusters, remains largely unaffected. The universe maintains its character. Dense pockets and extreme objects exist, but they are rare, and most of the volume is empty. Black holes illustrate the extremes of concentration within a dominantly empty cosmos. In clusters of galaxies, black holes contribute to heating and regulating gas through energetic jets. Supermassive black holes in active galactic nuclei release tremendous energy, shaping star formation and influencing galactic evolution. These interactions show how concentrated mass can exert power on its surroundings. Yet when compared to the cosmic scale, these regions are tiny. The majority of space remains an expansive void. Black holes demonstrate how matter can be tightly compressed and influential locally, while the universe at large remains sparsely filled. The contrast between concentrated gravity and surrounding emptiness is striking. Even in the densest clusters of galaxies, black holes are sparse. The number of black holes is tiny compared to the number of stars or planets, and they are separated by vast distances. Most photons, particles, and dark matter pass through intergalactic space without encountering these extreme objects. The voids dominate the volume. The presence of black holes does not compromise the overall emptiness. Their rarity emphasizes how unusual concentrations of matter are in a universe where empty space accounts for the overwhelming majority of volume. Matter is exceptional, not typical. Black holes also help define the shape and stability of galaxies without filling the cosmos. They anchor central regions, control orbital patterns, and regulate the inflow of gas. Their gravitational pull is essential for galactic structure. Yet beyond these localized spheres, the universe resumes its emptiness. Distances between galaxies are enormous, and the space within them is mostly empty as well. Black holes serve as reminders that while matter can be concentrated, the spaces in between remain vast and undisturbed. They highlight the contrast between localized density and universal sparsity. On the larger scales, the contrast becomes even more apparent. Superclusters, filaments, and walls contain galaxies with black holes at their centers, yet these structures occupy only a small fraction of the observable universe. The distances between filaments, the voids that stretch for hundreds of millions of light years, dwarf the sizes of even the largest black holes. Space is defined more by absence than presence. Matter is clumped and concentrated in rare regions, but the volume of voids overwhelmingly dominates. Black holes, powerful and extreme as they are, exist as minute points in an otherwise empty expanse. The distribution of black holes across the universe reinforces the sense of sparsity. Many galaxies contain a central supermassive black hole, but countless regions of space are entirely free of such objects. The majority of the universe is not under the direct influence of a black hole's gravity. These empty regions span light years, sometimes hundreds of millions of light years, between the nearest dense structures. The presence of black holes in certain locations accentuates how rare and exceptional matter concentrations are in the cosmos. Most of what exists is empty space. Gravity itself, while central to the formation of black holes, does not fill space. It acts across distances, weakening with separation and allowing enormous voids to remain untouched. Black holes concentrate mass to extremes, yet gravity alone cannot fill the gaps between galaxies or clusters. Matter, no matter how dense, occupies only small regions. The universe is structured by gravity but defined by emptiness. Black holes represent peaks of density in a landscape that is overwhelmingly flat, sparse, and empty. Their existence highlights the extremes of matter while reinforcing the dominance of nothingness. Even as black holes consume nearby matter, they do not threaten the vast emptiness beyond. The accretion of gas, stars, and dust occurs in localized regions, and the effects diminish rapidly with distance. The universe continues to be a place where empty space vastly outweighs occupied regions. Black holes are islands of concentrated matter, but their rarity emphasizes how exceptional matter is in a mostly empty cosmos. This juxtaposition of extreme density and overwhelming void provides a clear perspective on the nature of the universe. It is filled with matter in some places, but space itself remains the dominant feature. The contrast between black holes and surrounding space also offers a sense of scale. While the event horizon of a supermassive black hole may span billions of kilometers, the distance to the nearest galaxy is millions of light years. The ratio between dense concentration and empty space is immense. Matter is compressed into tiny points, yet the voids continue indefinitely. Observing black holes, their formation, and their interactions helps us understand how matter behaves under extreme conditions. At the same time, it reminds us that for every concentrated object, there are vast expanses of empty space surrounding it. The universe is overwhelmingly nothing, punctuated by rare islands of extraordinary density. The presence of black holes completes the picture of matter in the universe. They show how matter can be concentrated and powerful locally, shaping stars, gas, and galaxies. Yet even these extreme objects occupy only an infinitesimal fraction of the total volume. The rest of space stretches endlessly, mostly empty, shaped by dark energy and filled with the quantum vacuum. Black holes illustrate the rare exceptions to emptiness, the points of intensity in a vast landscape of nothing. The universe is dominated by empty space, and black holes stand out as rare, concentrated anomalies in this expansive void. When we look at the universe, we see only a portion of the whole. This is the observable universe, the sphere around Earth from which light has had time to reach us since the Big Bang. Its radius is roughly 46 billion light-years. Beyond this boundary, there may be more space, more galaxies, and more matter that we cannot see. The observable universe gives us a window into cosmic history, yet it is just a fraction of the total. Space likely stretches far beyond what we can detect, possibly infinitely. This unseen expanse is a vast canvas of emptiness, largely inaccessible to observation, yet it defines the scale of cosmic voids and the rarity of matter. Cosmic topology, the shape and structure of the universe, helps us understand its geometry. Observations suggest the universe is flat on large scales, meaning parallel lines remain parallel, and triangles add up to 180 degrees. A flat universe implies that space can extend without limit, creating enormous voids between clusters and filaments. Some theories suggest the universe may loop or curve subtly on extremely large scales. But whatever its global shape, the vast stretches of emptiness persist. Matter is concentrated in islands, galaxies, clusters, and filaments. The rest is open space, stretching continuously in every direction. Curvature and topology influence how light travels, how structures evolve, and how expansion behaves over time. Even in a flat universe, expansion driven by dark energy continues indefinitely. The large-scale structure, the cosmic web of galaxies and filaments, exists within an ocean of empty space. The distance between clusters grows constantly, and voids expand faster than new matter can occupy them. This means that emptiness increases not just in volume, but in relative importance. Galaxies form and persist, yet they are isolated within a growing expanse where matter is exceptionally rare. The fate of the universe is tied to this expansion, and to the behavior of matter and energy across space. In trillions of years, cosmologists predict a state known as heat death. Stars will burn out, black holes will slowly evaporate, and the universe will approach thermodynamic equilibrium. All processes that create energy differences will end. Matter will continue to exist in tiny islands, but the density of the universe will approach zero. Space itself will dominate entirely, filled with the quantum vacuum and dark energy, almost devoid of matter and radiation. Emptiness will become absolute, not just vast, but universal. Even before heat death, the expansion driven by dark energy stretches voids and distances to enormous scales. Galaxies that are not gravitationally bound to us will recede faster than light, effectively disappearing from observation. The observable universe will shrink in practical terms, though space itself grows. The large-scale geometry ensures that matter remains isolated in clusters, surrounded by ever larger voids. Sparse structure will persist, but the spaces between these islands will define the universe. Emptiness is not an occasional feature. It is the default state, the overwhelming majority of volume. As time moves forward, the role of matter diminishes. Ordinary matter, already a tiny fraction of energy density, becomes more diffuse. Dark matter continues to shape local gravitational wells, but the expansion stretches the distances between these wells. Filaments become thinner, clusters more isolated, and voids encompass greater volumes. The large-scale structure of the universe is like a lacework of matter suspended in an endless sea. Even the strongest gravitationally bound systems cannot fill the voids around them. The universe is largely empty, and this emptiness will dominate increasingly as cosmic time advances. The geometry of the universe also emphasizes the perception of emptiness. On smaller scales, galaxies and clusters may appear dense, with stars close together relative to the space they inhabit. Yet on cosmological scales, these structures occupy only a tiny fraction of the total volume. Light from distant galaxies travels through vast voids, often millions of light-years wide, before reaching observers. The observable universe is a collection of rare pockets of matter floating within an immense and growing nothingness. The majority of space is untouched, empty, and unobservable, highlighting the dominance of emptiness. Heat death illustrates the ultimate extent of nothingness. Over trillions of years, processes that concentrate energy and create structure will cease. Black holes will slowly lose mass through Hawking radiation. Stars will extinguish, leaving cold remnants. Galaxies will drift apart, no longer forming new stars. The observable universe will consist of isolated remnants surrounded by immense stretches of empty space. The volume occupied by matter will shrink relative to the vast expanse. Space itself, energized by the quantum vacuum and stretched by dark energy, will prevail as the primary feature. Nothingness becomes the permanent condition of the cosmos. Even as the universe ages, sparse structure persists. Stars, remnants, and black holes remain in tiny regions, held together by gravity. Yet the regions between them expand without limit, ensuring that matter remains exceptional. Clusters become isolated islands in a vast ocean of empty space. Light from distant structures may never reach other parts of the universe. The cosmic voids will dominate not just in volume, but in terms of influence on cosmic evolution. Matter exists, but it is surrounded by an overwhelming majority of nothingness. This interplay between concentration and emptiness continues to define the observable universe. Galaxies, clusters, and filaments are meaningful features, yet they are rare. The large-scale geometry, the expansion, and the predicted fate of the universe confirm that the spaces between structures are far more significant. The distances are enormous, and matter occupies only a tiny fraction. Even when structures persist, the empty regions determine the character of the universe. The observable cosmos is a patchwork of matter islands in a vast, nearly empty ocean, emphasizing the extraordinary sparsity of matter. The growth of empty space affects observation and measurement. As cosmic expansion proceeds, light from distant galaxies is stretched and redshifted. The farther objects are, the more their light is diluted by the intervening void. Eventually, many galaxies will recede beyond observation entirely, leaving a horizon defined by emptiness. Cosmic topology ensures that these voids are continuous, connecting the observable universe with unobservable regions. Matter is confined to rare clusters, surrounded by space that is almost entirely empty. Observers in the future will see even greater emptiness than we do today. In conclusion, the universe's large-scale geometry demonstrates the scale and dominance of emptiness. The observable universe reveals that matter, while essential for galaxies, stars, and planets, occupies a minuscule fraction of space. Voids between structures are vast. Cosmic expansion stretches these regions further, and the future of the universe promises heat death, isolation, and extreme sparsity. Even as matter persists locally, the majority of volume is, and always will be, empty. The universe is defined more by the absence of matter than by its presence, emphasizing that nothingness is the prevailing condition across both space and time. Looking out at the night sky, humans sense a vastness that far exceeds daily experience. Stars appear as points of light, galaxies as faint smudges, yet the spaces between them are enormous. The distances are so great that light from some galaxies takes billions of years to reach us, crossing emptiness that dwarfs anything familiar on Earth. Mountains, oceans, and cities occupy measurable space, but these scales are minuscule compared to the voids of the cosmos. Even within our own solar system, the space between planets is largely empty, a silent stretch where photons move freely and particles are few. The universe is overwhelmingly empty, and human perception struggles to comprehend this vast nothingness. The emptiness becomes more apparent when considering the scales involved. Earth itself is small, a tiny sphere floating in a solar system where the nearest star is 4 light-years away. Our galaxy is immense, yet it is only one of hundreds of billions in the observable universe. Between galaxies lie voids that are hundreds of times larger than the galaxies themselves. In these regions, matter is so sparse that a single atom might occupy cubic meters of space. Radiation, dark matter, and the quantum vacuum fill the rest, creating a medium that is not truly nothing, yet devoid of the familiar objects and structures that define human experience. The universe is dominated by these empty expanses. Every region of space, even those that seem occupied, contains far more emptiness than matter. Within atoms, the nucleus takes up only a tiny fraction of the volume, surrounded by electrons moving in probabilistic clouds. Matter itself is mostly empty, and when scaled up, the sparsity becomes extreme. Planets, stars, and galaxies are concentrated islands within a vast ocean of emptiness. Gravity, radiation, and dark energy operate across these spaces, shaping the motion of matter and the expansion of the universe. The majority of existence is not composed of objects, but of the spaces between them, forming the stage upon which all cosmic activity unfolds. Human experience is confined to environments that feel solid and dense. Walking through a forest, swimming in the ocean, or moving through a city gives the impression of full, continuous space. Yet even in these familiar contexts, the atomic structure of matter reveals vast emptiness. The feeling of solidity comes from electromagnetic forces between atoms, but the volume of empty space inside them is enormous. When this perspective extends to the cosmos, the scale of emptiness grows exponentially. Stars, clusters, and filaments are concentrated masses, but the universe as a whole is overwhelmingly a vacuum. Human intuition is inadequate to grasp the scale, yet scientific observation provides clarity. The emptiness of space is not silent in the sense of inactivity. The quantum vacuum is alive with fluctuations. Photons travel for billions of years, and dark energy drives expansion. These aspects of nothingness demonstrate that the void is dynamic, not inert. Black holes bend space, clusters influence their surroundings, and cosmic expansion stretches the fabric of space itself. Yet the volume affected by matter is extremely small compared to the total. In every direction, light and energy move through largely empty space, carrying information across unimaginable distances. The void is the backdrop against which all structure, motion, and observation occur. This perspective encourages a re-evaluation of presence and absence. Matter, though essential for stars, planets, and life, is exceptional. It occupies only a fraction of the universe. Emptiness dominates, yet this emptiness is not a void of possibility. It allows light to travel, particles to interact over vast distances, and forces to operate across the cosmos. It is the framework that supports cosmic evolution. Human perception often conflates emptiness with insignificance, but scientific understanding reveals that these vast spaces are integral to the workings of the universe. Without empty space, structure, motion, and life as we know them could not exist. The human mind, accustomed to dense environments, finds it difficult to imagine the scale of cosmic emptiness. Even the largest human-made structures are negligible on this scale. Distances are measured in light years, not kilometers, and volumes are so vast that ordinary matter is scattered in tiny, isolated islands. Clusters of galaxies, which appear immense, are separated by voids hundreds of millions of light-years across. Cosmic expansion is steadily increasing these distances, making matter even sparser. The universe is overwhelmingly empty, a reality that challenges perception and evokes a sense of awe grounded in measurement and observation rather than dramatization. Despite the emptiness, this space is not meaningless. The quantum vacuum, dark energy, and the gravitational influence of matter all operate within these voids. They guide the formation of galaxies, the motion of stars, and the propagation of light. Emptiness is the canvas on which cosmic events unfold. Stars ignite, planets form, galaxies rotate, and black holes anchor dense regions, all within a medium that is mostly empty. The dominance of nothingness provides both context and contrast, allowing matter to stand out and cosmic processes to occur without interference. The void is the essential backdrop for everything we observe. Considering human existence within this context emphasizes the extraordinary rarity of matter. Our planet, solar system, and galaxy are tiny pockets in a universe where the overwhelming majority of volume contains no ordinary matter. Even dark matter and dark energy, which constitute most of the universe's mass energy, are distributed sparsely in comparison to the volume of space. The cosmos is primarily a stage of empty space, punctuated by rare islands of concentration. Every star we see, every galaxy we study, exists within this immense backdrop of near nothing, making the presence of matter and life itself remarkable in scale. Observing this emptiness scientifically leads to awe without dramatization. Measurements of the cosmic microwave background, galaxy distributions, and gravitational effects consistently confirm that space is mostly empty. Photons traverse light years of void. Matter forms only in small fractions, and the universe continues to expand, stretching the nothingness further. The scale of emptiness is so vast that human intuition struggles, yet the scientific picture is clear. The universe is overwhelmingly composed of empty space. This space is active and dynamic, but it remains devoid of ordinary matter for the majority of its volume. The perspective gained from studying the cosmos underscores the difference between familiar environments and cosmic reality. Where humans experience solidity, density, and immediacy, the universe is characterized by emptiness and separation. Even clusters of galaxies, the largest structures visible, are isolated by millions of light years of void. The emptiness dominates both in volume and in functional importance, forming the medium in which light, gravity, and quantum effects operate. Structure exists, but it is rare. Space itself is the prevailing feature, the foundation upon which everything else rests. Understanding this vast nothingness reshapes our view of existence. Nearly all of the universe is empty space, yet this emptiness is essential. It allows photons to travel, gravity to guide matter, and cosmic expansion to proceed. Structures form, evolve, and interact precisely because they are embedded in a medium that is largely void. The vacuum, dark energy, and sparsely distributed matter create the dynamic stage for cosmic history. What seems like nothing is in fact a critical component, providing both room and context for the complexity we observe. The void is not inert. It is the framework of the cosmos. Even when contemplating life, planets, or galaxies, the scale of emptiness provides perspective. Human presence, planetary systems, and even galaxies are islands of matter floating in a vast ocean of nothing. Light travels unimpeded across enormous distances, and the quantum vacuum pulses with subtle energy. The universe is overwhelmingly empty, and yet this emptiness allows complexity to arise. Stars shine, galaxies rotate, and matter coalesces, all against a backdrop that is mostly void. Emptiness is not absence in the sense of inactivity. It is the dominant medium of existence, shaping and enabling everything we observe. Considering the universe in this way offers a scientific, awe-filled understanding of nothingness. Matter is rare, concentrated, and exceptional. The vast majority of space is empty, yet this space is active, dynamic, and essential. Black holes, stars, galaxies, and clusters exist within it, but they occupy only a tiny fraction of the volume. The void forms the stage for cosmic evolution, allowing energy, gravity, and radiation to operate across unimaginable distances. Observing, measuring, and understanding this emptiness provides a clear, thoughtful perspective. The universe is mostly nothing, yet this nothing is the medium for all that exists.